Hello everyone and welcome to the very first class in the first term of the SS3 Physics curriculum. Now SS3 students, what you have to do here is the rounding off of all you have learned in physics. Now some of the things we're going to be looking at involve some of the things you have done in past, so it's important that you revise those topics you've learned before now. And please feel free to revise with a plethora of our videos that you can find right here on our channel. Please ensure that you go through them, and if you do have any question, remember that we are always here for you. You can always put your questions in the comment section of any of our videos, and we promise to attend to all of your questions. Now, the very first topic you're going to do here is called electromagnetic waves. Now, this is something that is not new to you. During your time in SS2, you were introduced to wave energy, where we talked about classification of waves, where we have the mechanical waves and electromagnetic waves. Now, you see, these electromagnetic waves is very important to your studies, as they have a lot of uses, a lot of applications that is expected of you, that you should understand them, be able to explain them, and even use them in some cases. So we'll be talking more on them in this video, and these are the aspects that we're going to be looking at. So the first thing we'll do is we'll define waves again, so that we recall what we have learned in time past, so that we do not forget what waves are, and then we look at the types of waves when we talk about the classification of waves. Then we dive directly into the topic itself, where we will then define electromagnetic waves and explain how electromagnetic waves are propagated. Now, after we've done that, we'll then be looking at arrangement of electromagnetic waves by order of frequency and wavelength. Now, you see, unlike every other wave, there are some similarities to all electromagnetic waves, and there are some differences. So we always have to arrange them by order of their frequency and their wavelength, so that we can tell their penetrating power amongst every other things that describe electromagnetic waves. And at that point, we'll be looking at a simple acronym that will help you remember it. So it's not something that will be too difficult. It's not rocket science. We'll keep it as simple as possible, so that you can always recall it whenever it is asked of you. Now, after that, we'll then go to the important aspect of this lesson, which is the uses of electromagnetic waves. Just like I've said before, electromagnetic waves has a lot of applications that are very important to every student. So we'll be looking at these applications. How do we use electromagnetic waves? In which fields are they used? Remember now that we have different examples of them. So all of them have their various applications, and then we'll exhaust those applications and see which one are we using presently, which one is used around us that we do not know, and how can we use the properties of these waves to our own advantages. Okay, and then when we finish with that, we'll then solve some problems on electromagnetic waves. Now, many will be waiting for this part where you'll be looking at different questions from the WAEC exams, JAMB exams, and every other exams like that. But it's also important that you pay attention to every detail that we'll be looking at throughout this video. So please, you do not want to miss any of this. And we are also pleading with you that you do help us to reach many more students like you who need the kind of helpful content that we are creating right here on this channel, by sharing our video and engaging on the video by liking them and also dropping comments. So you can always drop a comment, and if you have any question also, please drop it in the comment section and we'll attend to all of your questions. So now, if you're ready, get your materials ready, because you really need to put some things down so you do not forget as you dive into the world of electromagnetic waves. Now let us recall what a wave is. So can you define a wave? Now, if you can take a moment, write down your definition for a wave, and then we'll look at it together and then see what a wave is. Now, we'll be looking at the basic fact of what a wave is. Now, some of the things you should recall is this. First off, a wave is a disturbance, right? I remember whenever I try to remember what a wave is, one memory that always comes to mind is this wave that happens when you throw a stone into a puddle of water. Now you begin to see ripples as they move from the point where the stone hits the puddle. You see those waves moving away from that point to the edges of that puddle. So you see there that it was created when you disturbed the peaceful demeanor of that water surface. The water seemed calm at the beginning. Then you disturbed it by throwing a stone into it, and then that created what? A wave. Okay, so you see, a wave is a disturbance. But one other thing that it does is that it transfers energy. Now, what it does is it transfers the energy from one point, the point of disturbance, to any other point on that body, but it does not permanently displace the particles of the medium. Now, you see, all these things mentioned here is what comes together in the definition of a wave. So let's write down what a wave is. A wave is a disturbance which transfers energy through a medium without any permanent, this should be E, permanent displacement of the particles of the medium. So let's go over this definition one more time. A wave is a disturbance which transfers energy through a medium without any permanent displacement of the particles of the medium. This is how we define wave. Now, aside from the wave you see when you throw a stone into a puddle of water, there are several other examples of waves. Now, some of them we can see with the physical eye, some of them we cannot see with the physical eye, which means that when we begin to discuss wave, there are different classifications of waves. Now, we're going to look at this exhaustively, okay? But one of the things you should recall at this point is that when we are looking at waves, you are either classifying it based on the propagation or you are classifying based on the material medium, whether it requires material medium or not. Now, if you do recall, you see that we have it as either transverse or longitudinal wave, and then we also have it as either mechanical or electromagnetic wave. Now, the part that is important to this video is the electromagnetic waves, but we should not forget all the various classifications. But before we go into classification, let us look at this definition one more time so that it sticks. A wave is a disturbance which transfers energy through a medium without any permanent displacement of the particles of the medium. When it comes to the classification of waves, there are two main groups or subclasses of waves that we have. The first one is when we classify waves based on the direction of vibrations of the particles and the direction of the wave, and that gives us either transverse or longitudinal waves. So waves can be classified as transverse or longitudinal. Now, what does it mean when we say a particular wave is transverse or when we say a particular wave is longitudinal? Let's differentiate them. So starting with what a transverse wave is. Transverse waves. So when it comes to transverse wave, what you observe is this. Now, in the case of a transverse wave, you'll find that, remember that the wave itself is a disturbance, right? So when the disturbance creates a wave, you see that the particles of the medium through which energy is transferred by the wave would be vibrating in a direction that is perpendicular to the direction of the wave itself. Now, one of the examples of a transverse wave is water wave. So to explain this, let's consider when you take a stone and then you throw it into a puddle of water. Now, what you observe is that at the point where the stone lands, a disturbance creates a wave there, right? Now, the wave will then be moving along the surface of the water puddle. Okay, so that would be the horizontal plane, horizontal direction. The wave is traveling horizontally. However, when you place a material that will float on the water on that wave, what you observe is that that material, say like for example a plastic bottle on the water, you see that it begins to bob up and down, showing that the particles of the medium are vibrated along the vertical plane. Now, don't forget, the wave is traveling where? Along the horizontal plane, while the particles of the water here is traveling along the vertical plane. That is right angle to each other, so they are perpendicular to each other. That kind of wave is said to be transverse in nature. Okay? So, but don't forget, when we were describing what a wave is, we defined wave as a disturbance that transmits energy through a medium without permanently displacing the particles of the medium. So despite the fact that the particles are moving, they are not displaced from their original position. They just bob up and down. So they remain at that point, bobbing up and down. They do not travel with the wave. Okay, so the particles of the medium that propagates the wave are not permanently displaced. They are only moved up and down. By the time everything settles down, they remain at the original position where they are because they are not permanently displaced. Okay, so but what you see here is that what? The direction of their motion is what? Perpendicular, that is at the right angle with the direction of the wave. So let's put down the meaning of transverse wave now. A wave is said to be transverse when the particles of the medium vibrate perpendicularly to the direction of the wave. So like in the case of the water wave, the vibrations of the particle is perpendicular, that is at 90 degrees to the direction of the wave. So examples include water waves and all electromagnetic waves. Now, by the time we talk about electromagnetic wave, we are going to expand on this in more detail. But for now, please note that when you have a wave such that the vibrations of the particle of the medium where the wave is being produced is traveling or vibrating in perpendicularly to the direction of the wave, that is at right angle or 90 degrees to each other, such a wave is said to be transverse. Now, the other group we have here in this subclassification of wave is the longitudinal wave. So let us look at what a longitudinal wave is. Longitudinal waves. Now, it's a different case when you compare it with transverse wave. Transverse wave, the direction of the wave is perpendicular to the vibration of the particles. But for longitudinal, the vibration of the particles and the wave are parallel to each other. So let's put that down. A wave is longitudinal if the particles of the medium producing the wave vibrate in a direction parallel to the wave. Okay, so in this case here, you see that the vibration of the particles is in a direction that is parallel to the direction of the wave. That is, they are moving in the same direction. They are not separated by any angle, so they cannot meet. So the direction is parallel to each other. Now, examples here include sound wave. The sound wave is a longitudinal wave. That is, when sound waves are produced, the vibrations of the particles of the wave is parallel to the direction of the wave motion itself. So this is how we separate waves from being transverse or being longitudinal. But this is not the only classification of wave that we have. So let's look at another set of classification of waves. The other group to which we classify waves is when we classify wave as either mechanical or electromagnetic. So waves can also be classified as mechanical or electromagnetic. So when we talk about electromagnetic waves, sometimes you may see it as EM waves. So EM there stands for electromagnetic. Now, since that is the main purpose of this video, where we are looking at electromagnetic waves, so along the course of the video, you will see me use the word EM as we go on. So when you see EM, just know it stands for electromagnetic. But when we say a particular wave is mechanical, and then we say another wave is electromagnetic, what does it mean? Let's start with mechanical waves. Mechanical waves. Now you see, there are some set of waves that require material medium for their propagation. That is, for example, when we look at examples of mechanical waves, such as water wave, such as sound wave, such as wave in strings, waves in pipe. These particular waves that we mention here would not have been propagated without the vibrations of particles of that medium. So you require the particles of the medium through which the waves is produced to be vibrated for such waves to be able to be propagated from one point to another. So they require material medium. Let's put that down. These are waves which require material medium for their propagation. And examples are water waves, sound wave, waves in strings, etc. Now, you see these waves require material medium for their propagation. Like in the case of water wave, when you throw a stone into a puddle of water, what you observe is that the molecules that constitute the water puddle that you have thrown the stone into, which appear calm at the initial, they begin to vibrate along a plane. So they begin to vibrate up and down like that for the wave to be propagated from the point of disturbance to the edge of the water. So it needs the molecule of water for its propagation. And the same thing applies to sound waves, depending on where it is produced. If sound waves is produced in the atmosphere, in a place with atmosphere, it requires air for its propagation. Sound wave can also be produced in water and in solids. Like in the case of water, you need the water molecules for you to transmit the sound wave. And for solid objects like the drums, percussion instruments, when you strike them, they produce sound. The same thing when you hit your hand on a table or any solid object. What follows immediately is a sound that is produced, which is as a result of the disturbance of that solid object, leading to the vibrations of the molecules that constitute the solid. So you see, sound wave requires the vibrations of the material medium through which it is propagated. And of course, if you want to analyze that, you see that when the particles vibrate, it produces the sound, and then the sound can then be transmitted through air also to your hearing. Okay, so you see that multiple molecules are being vibrated for you to be able to perceive the sound when you hit a drum. So that's the case for sound wave. And then for waves in string, as you guessed it, yes, it requires the vibrations of the molecules that constitute the string for the waves itself to be propagated. So in general, any wave at all that requires material medium for its propagation, then that wave is mechanical. Now, here's a slight twist here. Please take note. You can have mechanical waves that are transverse in nature, and you can have mechanical waves that are longitudinal in nature. I mean, take a look at this. Water wave is an example that was given when we were talking about transverse wave. So water wave, despite the fact that it's a mechanical wave, it is a transverse wave as well. And then when you look at sound wave is a longitudinal wave. So it is mechanical and longitudinal. What this means is that mechanical wave can either be transverse in nature or longitudinal in nature. Now let's go to the next one, which is electromagnetic wave. Like I mentioned earlier, you could also see things in some books where it will be written as EM waves. Don't forget, E will stand for electric and M stands for magnetic. Now, why this is so is because when we say electromagnetic waves, we are looking at two fields here that are combined together. The electric field and the magnetic field, which when combined together produce what is known as the electromagnetic field and then the electromagnetic wave when you look at disturbance within these two fields. Okay, so now how we describe electromagnetic waves are those particular waves that do not require material medium for their propagation. Now let me tell you something here. You see, in the case of sound waves, water waves and all these things, they cannot be produced in a vacuum because they require material medium for their propagation. Whereas when you have electromagnetic waves, you can produce them in vacuum. Let me give you examples here. When you talk about light wave, that is the visible wave, when you talk about X-rays, when you talk about gamma rays, radio waves, and all forms of electromagnetic waves, examples of electromagnetic waves. All these waves can be produced in vacuum. And a vacuum is a space where there is nothing, it's empty. There is no particle at all within that space. Yet, you can propagate these examples of electromagnetic waves that I have mentioned in that kind of a space. But a sound wave cannot be produced in that kind of space. So that tells you sound wave require material medium. That is why it is mechanical in nature, of course. And then electromagnetic waves do not require material medium for their propagation. So let's put that down. These are waves which do not require material medium for their propagation. And examples include all well, when we're talking about examples of electromagnetic wave, we're looking at examples such as the radio waves. The radio waves are examples of electromagnetic wave, X-ray, visible light, etc. Now, all of these waves, the radio wave, X-ray, gamma ray, visible ray, ultraviolet, and the likes, fall under the classification known as the electromagnetic waves. So don't forget, we have mechanical wave and we have electromagnetic wave. Now, an extra thing that you should know, a tip that you should have handy is this. Remember that I mentioned earlier that mechanical waves can be either transverse or longitudinal. For electromagnetic wave, all the electromagnetic wave that we know are transverse in nature. So all electromagnetic waves are transverse. You can't find any that is longitudinal. But to recap what we have learned so far, when it comes to classification of wave, you can classify as either transverse or longitudinal, and then you can also classify as either mechanical or electromagnetic. And don't forget, if you have any question at all, please feel free to put it in the comment section and we'll attend to all of your questions. When it comes to electromagnetic waves, that is the kind of waves that do not require material medium for their propagation, there are three characteristics that every student needs to be aware of. Now, these characteristics come into play especially when you compare and contrast between electromagnetic waves and mechanical waves. And you can find them in several questions that are on either electromagnetic waves or the mechanical waves. So let us learn these three characteristics of the electromagnetic waves. Now, the first characteristics here is in terms of the electric magnetic fields that are present in the EM waves. So you see, in EM waves, the electric and magnetic field are mutually at right angles to each other and the direction of the wave. So that is when you consider an electromagnetic wave. You see the electric part, the magnetic part, and the direction of the wave. All these three are mutually at right angles, that is 90 degrees to each other. Now, this is what I'm saying here. Okay, in an electromagnetic wave, you see that perhaps if this line here represents the electric field, and this line here be the direction of the wave, okay, you see that at right angle to this on a plane, kind of like your length, breadth, and height kind of thing. You see that they are mutually at right angles to each other. Okay, these are at right angles to each other. So you could have this as the electric, the magnetic, and then the waves. All these three are at 90 degrees, mutually at 90 degrees to each other. That's what these characteristics imply. Now, the second characteristics we also have to be that we have to know is as regards to the speed of the wave. Now, please take note that when we're talking about waves in our SS2 class, we did mention things like speed of a wave, frequency of the wave, wavelength of the wave, all of these still matter, okay? So in the case of electromagnetic wave, all electromagnetic waves travel at a speed known as the speed of light. So let's talk about this. All EM waves travel at the speed of light. And you see, the speed of light itself, speed of light, C, equals 300,000 kilometers per second. That is, every electromagnetic wave that you know can travel 300,000 kilometers in just 1 second. Okay, that's the speed at which they travel. And we're going to write this in the proper SI units, which is in meter per second. We will say this is equal to 3.0 times 10 to the power of 8 meters per second. This is why it is often said that when you are studying electromagnetic spectrums or electromagnetic waves, sometimes you are looking back in time. Like for example, okay, when you look at the sun, okay, the sun is the star in our solar system, the star that is central to our solar system that we see during the daytime. You see, the light you see that comes from the sun has actually traveled from the surface of the sun to the surface of the earth where you then see it, okay? And this distance here, it takes light about 8 seconds to complete that distance. So when you see the sunlight, note that that light that you are seeing has traveled for 8 seconds. So when you look at the sun, you are looking at the sun as it was 8 seconds ago. That's a kind of way of time traveling, okay? Because you are seeing the sun the way it was 8 seconds ago, not the way it appears right now. And the same thing applies to when you're looking at other celestial bodies in the outer space. When you look through the telescope or when you look at stars that are twinkling away in the night sky, some of the light you see from those stars have traveled for millions of years just before you could see them. So you are actually looking far back in time. This is why when distances are measured in space, they are measured in something known as light year. And light year is actually the distance that light travels in 1 year, despite its speed. So when we say 1 light year, you're looking at the distance that light has traveled in 1 year, which is in millions of kilometers, okay? Trillions sometimes. So many of the things you see, like the Andromeda galaxy, amongst other space objects that you see in the night sky or with the aid of a telescope, all of these lights you see are things that were produced many years before you actually saw them, depending on their distance from Earth, okay? So that's in the case of the second characteristics of electromagnetic waves. So don't forget, speed of light is 300,000 kilometers per second or 3.0 times 10 to the power of 8 meters per second. Now to the third and final characteristics that every student must know of electromagnetic wave is that all electromagnetic waves that we know are transverse in nature. So all EM waves are transverse. Now, I did mention that when it comes to the characteristics of EM waves, we can use them to compare and contrast with mechanical waves. So let's pick it now from the back to the front. We ended here with all EM waves are transverse. This does not mean that mechanical waves are then the opposite, which is longitudinal. No, not at all. Okay? What this means is that all electromagnetic waves are transverse in nature. But when you learn about mechanical waves, you will find that some mechanical waves are transverse, just as some mechanical waves are longitudinal. An example of such, water wave is a mechanical wave and it is transverse, while sound wave is also a mechanical wave, but it is longitudinal. So you see here now, despite the fact that all EM waves, all electromagnetic waves are transverse, mechanical wave can be either transverse or longitudinal. So that helps you when you are comparing and contrasting between mechanical waves and electromagnetic wave, beyond the fact that mechanical waves require material medium for their propagation and the electromagnetic wave do not. That's actually one of the differences. Okay, another difference is in the case of electromagnetic wave being transverse, while mechanical wave can be either transverse or longitudinal. Now another is in the case of the speed. Don't forget here that we've mentioned that all electromagnetic waves travel at the speed of light. When it comes to mechanical wave, however, they travel at a speed that is less than the speed of light. Now they vary. So there's no particular speed for mechanical wave. So that's why we just say they travel at a speed that is less than the speed of light. You find some of them traveling at high speed, some traveling at low speed. I mean, even in some kind of mechanical wave, you can find different speed depending on the material medium through which they are being propagated. Like for example, sound wave. Sound wave through solid can travel at speed that is as high as 5,000 meters per second. But when you transmit sound wave in water bodies, it can travel as high as speeds of 1,500 meters per second. See that? From 5,000 to 1,500. And then when you transmit sound wave in air, it travels at maximum speed of 340 meters per second, which is significantly less compared to the other speeds that we've mentioned. And when you compare all of this speed with the speed of light, you see that they are far from it. Okay, so they are very much low than compared to the speed of light. Okay, but the speed of this particular wave, now that is a mechanical wave, varies depending on the medium through which it is transmitted. Okay, so don't forget, mechanical wave travel at the speed less than the speed of light, while electromagnetic wave travel, all of them travel at the speed of light. And the value of the speed of light is 300 kilometers per second, or 3.0 times 10 to the power of 8 meters per second. And then finally here, in this case here, when we talk about electromagnetic wave having the electric and magnetic field, that does not exist in the case of mechanical wave at all. So when you compare and contrast between mechanical wave and electromagnetic wave, aside from the fact that mechanical wave require material medium while electromagnetic wave do not require material medium, you can also mention other cases in terms of the speed at which they travel, and also whether they are transverse or longitudinal, just as I have explained so far. So that's it on the characteristics of electromagnetic wave. Let us now look at electromagnetic waves in the order of their frequencies and wavelengths. Now, if you check out the video where we talked about the different types of waves, we did see that regarding the properties of waves, we look at things such as the speed of a wave, the frequency of a wave, and the wavelength of a wave. So we often denote wavelength as lambda. We denote the wave speed as either v, but in electromagnetic wave we denote it with c, which is the speed of light, which is a constant at 300,000 kilometers per second, or 3.0 times 10 raised to the power 8 meters per second. But you see the frequency and the wavelength. The frequency is denoted f, wavelength lambda. They vary, they change depending on the particular electromagnetic wave that you are looking at. So when it comes to electromagnetic wave, you can either arrange it in increasing order of frequency or in decreasing order of wavelength as follows. Okay, so when it comes to electromagnetic wave, there's this simple acronym that will help you remember them. Okay, here's now the thing. We remember it by using Revox G. Okay, but as we talk on this, I will mention a particular wave that is part of the radio wave, but because it has such a different functionality as compared to other radio waves that we know, we often separate it from radio wave. It does not mean it's not a radio wave. It is a radio wave, but because of the extra functionality it has, we tend to discuss it separately from the other radio waves. Okay, but what does Revox G mean? It's an acronym that helps us remember the arrangement or the order of electromagnetic wave in terms of frequencies and wavelengths. So when we arrange it like this, R stands for radio waves. Radio waves. As part of radio wave, we also have another one that is known as the microwaves. Okay, the microwaves is also a radio wave, but it has some special functionality as compared to other radio waves that we have. So this is why we discuss it separately from the radio waves. Okay, so we are still under R now. The next alphabet we see here is I in this acronym we have here. So I here stands for infrared. Infrared. Okay, the V stands for visible. Visible light. The U here stands for ultraviolet. The X here stands for X-ray. And then G here stands for gamma. Gamma radiation or gamma ray. Okay? Now, this particular order of arrangement, like this, now this arrow here indicates increasing order, increasing frequency. So that is, in this particular order, the one with the smallest frequency is radio wave. Microwave is also a radio wave, okay, and the frequency is within the same limit. Now, please take note. Radio wave is not a particular frequency. I would have given you the frequency in each case, but it's because they are not limited to a particular frequency. So we just group them as increasing order of frequency. Like for example, some radio waves are in about say 100,000 kilohertz. And then you can also find others that are lesser than that. Okay, those of you that are very familiar with radio stations, when you see there are some radio waves you see that are in megahertz. Okay, like the frequency for some radio stations that you see, sometimes you hear 88.9, you hear things like 92.5. Those are in megahertz. Megahertz of frequency. There are some radio waves that are lesser than that, like back in the days when radio transmission was done in AM waves. Okay, those ones are in kilohertz of transmission. I remember BBC back in the time was in kilohertz. We'll use that to listen to sports broadcasting, amongst other things like that. And you will be required sometimes to put your antenna at places that are very high so that it could be able to pick up the signal from BBC at that time. So those were the times, in time past. Right, but now we have radio frequencies that are higher than that and can be easily picked with even smaller antennas. Okay, so but radio wave is not limited to a particular frequency. We have a wide range of frequencies, a bandwidth of frequency. That's the word we use to describe the ranges of frequency for radio wave. It's called a bandwidth. So the radio wave frequency bandwidth exists. And within that bandwidth, we have the microwave at the extreme end of radio wave. So they have frequencies that are higher than your regular radio waves. So they are the close edge of the bandwidth limited for radio waves. Now, when you exceed that, you cross into another type of waves there, a spectrum, a new spectrum known as the infrared spectrum. Okay, and this one also has its own bandwidth. So a lower bandwidth to the upper bandwidth when you have the infrared waves spread across that particular bandwidth. And then the same thing applies to visible light. Okay, now in the case of visible light, I hope you know by now, if you don't know this already, please check out our video when we talk about light wave, especially in our SS2, the SS2 playlist. We talked about light wave extensively. And you will see that visible light, what we see as white visible light, is actually a collection of multiple colors. Okay, and then you see there's an arrangement we explained to you there where you can then see how lights can be arranged like the colors of the rainbow using the acronym ROIC-BIF. Okay, when you look at this, all of these make up what we know as white light. Okay, and the frequency is increasing from red to violet. Okay, it's their frequency changes. It's all under the same spectrum here, this visible light spectrum. All of them are arranged here, and they have their individual frequencies just as much as they have their individual wavelength. Okay, and then the next one you see after the bandwidth of visible light is the ultraviolet. Of course, it has its own bandwidth as well, just as X-rays also have its own bandwidth immediately after the ultraviolet bandwidth, and then finally it ends on the gamma rays. So of all these arrangements, the highest frequency is with the gamma ray. Gamma ray has the highest frequency, radio waves has the lowest frequency. Now, when you then arrange it in this direction, where the arrow is pointing upward, that is from gamma ray like this, that's in terms of their wavelength. Okay, so that tells you that the shortest wavelength is gamma ray. Okay, and the longest wavelength is radio wave. Now you see this wavelength and frequency also affect a characteristics of electromagnetic wave known as penetrating power. The shorter the wavelength, the more its penetrating power. Okay, so that tells you that gamma ray, X-rays, ultraviolet have more penetrating power as compared to the other waves. Okay, these ones can be easily blocked by small items, but you see, gamma ray can penetrate even heavy metals. X-rays can penetrate the body tissues. They are stopped by bones, amongst other things. When we begin to discuss the uses of this wave, you begin to see how the frequencies and wavelengths play into how we use them. But don't forget that in this arrangement, because these gamma rays have the shortest of wavelengths of all the electromagnetic wave, that also means it has the highest penetrating power. So that's why it's always advised that you do not expose yourself to radiations. Now, whether it's radio wave, microwave, infrared, all of these radiations, try to limit the way you are exposed to them. They can really cause a lot of dangers on your body. Okay, but depending on their penetrating power is what determines how much of a danger they are to you. So radio wave, for example, poses the least amount of danger as it has the least penetrating power. While the one that is most dangerous in this case is the gamma ray and X-rays. You don't want to be exposed to it. Even the ultraviolet can also be dangerous. That's why you see that many times people, when they go to the beach, they often coat their bodies with UV blockers because the sun itself emits the ultraviolet radiations, which is also dangerous to the skin. It can cause skin cancer amongst other kinds of dangers, skin burn and the likes. Okay, so this is why we always have to be shielded from all this radiation. But don't forget, the most harmful has the highest penetrating power, and that is gamma radiation. So if you're asked perhaps in an exam to mention electromagnetic waves in increasing order of frequency, the first you should mention is radio waves. That is radio waves and microwaves. Then next you have the infrared, then the visible, the ultraviolet, the X-ray, and finally the gamma ray. That is increasing order of frequency. Now, if you're going to do it in decreasing order of wavelength, it will follow the same pattern. Okay, because this is the longest wavelength and this is the shortest wavelength. So wavelength is decreasing down this direction. Okay, but when you follow this arrow, that is from gamma ray to radio wave, this will be increasing order of wavelength and decreasing order of frequency. So you see that now. It is a vice versa kind of a thing, okay? You can do it in terms of frequency, in terms of wavelength. So to recap, the shortest wavelength is gamma ray, and the longest wavelength is radio wave. Then in terms of frequency, the highest frequency is gamma ray, and the lowest frequency is radio wave. And that's the arrangement of electromagnetic wave in order of their frequencies and wavelength. As mentioned at the beginning of the video, that electromagnetic wave has a plethora of applications. That is, there are so many applications to electromagnetic wave. And since we've already looked at examples of electromagnetic waves in order of frequency and wavelength, let's just follow that same order and begin to look at the uses of these electromagnetic waves. Starting with radio waves. Now remember that I mentioned that microwave is also a radio wave, but because it has its own separate kind of applications that is a bit different from how we use the other radio waves that we know, I will be discussing the applications or uses of microwaves separately. Okay, so when I'm saying radio wave, it's with the exception of microwaves. Now, here are some of the ways we use the radio waves. We use it in communication, in navigation, in astronomy, in remote controls and security. But let me explain what this means. Now, in the aspect of communication, it is used in radio and TV broadcasting. Okay, so you see your radio and television broadcasting employs radio waves as a means of transmitting what is done in the TV studios, the radio studios. They record there and then they transmit it via radio waves. That is why you see your TV, your radio, they go through frequencies, radio frequencies from the source where they are produced to reach you, and then you receive them either from your TV or from your radio set. We also use it in mobile communications. Mobile communication. Telephones, your smartphones and the likes, all of them use radio wave. We also use it in two-way communications, two-way radio. In other words, what you know as your walkie-talkie. Okay, and the same thing for the police, the military and the likes. They also use radio wave to transmit their message. Okay, they connect it either through satellite communication, that is for the sat phones, or they use simple radio waves radio frequencies to transmit their message. Now, those of you that are very familiar with movies, especially the ones that has to do with investigations and the likes, you often see that whenever you see a police car, they are always fitted with a radio gadget there that receive radio frequencies that they use to transmit information. You hear things like a 1012 in progress, those codes that they transmit are something in progress, and then whoever the police officer that is using the car, once they receive that radio frequency, the message in the from the radio helps him to know what next to do in order to stop a crime in progress or to reduce the effect of a problem that is going on presently. So you see there that radio wave is employed for communication purposes. Okay, now in the case of navigation, we also use radio wave to help us move from place to place via what we know as the global positioning system. The global positioning system. Of course, this is what is shortened down to what we know as the GPS. So whenever you are traveling and then you employ GPS navigation, what you have done there is you have applied electromagnetic waves to help you locate your destination. So every time you say, Siri, I'm going to so place, and then it plots a journey track for you, you are actually applying the electromagnetic waves. The same thing when you use the Google Maps or any other kind of mapping system to navigate from one point to another, you have also employed the electromagnetic waves known as radio wave. Now, another one is in the case of astronomy. Now, astronomy also applies the radio waves also to transmit information from the space station, the International Space Station to Earth. Communication is done using radio waves through the satellites. satellite, and also satellite navigation. All of these are the applications of radio waves for astronomy. Now, in case of remote controlling, okay, there are some remote controls that actually employs radio waves for communication, from the remote control to the gadget itself. Like, for example, remote controls such as garage doors require radio frequency for communication. So when you click on the remote, the garage door opens. Okay, the moment it sends that frequency, it then opens. So you see here that the information that directs the garage door to open or close is transmitted via radio waves. And then there's another application in terms of security or identification, depending on the field where it is being used. Okay, you'll find some identity cards being fitted with something known as the RFID. The RFID is a chipset that transmits information via radio frequency. That's why it's actually called radio frequency identification. Okay, say for example in a school where all the students have RFID cards, you can know whether they've come into the school or left the school when they clock in their card at the gate. Okay, the same thing to so many industries where they have a lot of workers. Many of them carry identity cards that have been fitted with RFID tags. The same thing applies to transportation companies. Most of their vehicles have RFID fitted in them, especially for those that are transmitting valuable materials when they have to be identified when they get to their location. You want to be sure that the vehicle is the one that is carrying the particular luggage that you're expecting. So they may be fitted with RFID identifications like this, so that at the security post they can be identified to see whether it's the right vehicle or not. Okay, so whenever you use this type of system or any of these that we've mentioned here, what you are applying is the use of radio waves. So please put in the comment section any other way by which you could apply the use of radio waves. Now, in the case of microwave, which is also a radio wave, it has some extra applications which is quite different from how we use other radio waves. So this is why we are looking at it separately. Now, here are some of the uses of the microwave. It is used in cooking, in telecommunication, in radar, and astronomy. So in the case of cooking, it is used to heat food by vibrating water molecules. Now, many of you do have what is known as the microwave oven at home, where you put your food into it and then you put it on for some certain minutes, and then before you know it, the food that you have put into the oven becomes hotter than it was when you put it in there. You can use it to defrost food, you can use it to heat it up, you can use it to even cook some kind of food. Okay, and what it does, it basically applies microwave to vibrate the water molecules in the food that you have put into that oven, and that's how it works. Okay, now in the case of telecommunication, microwave is used in sat phones, used in satellite phones, Okay, whenever you are going to places where regular mobile telecommunication networks are not available, the sat phones has a wide range, whether you're using no matter the particular network you are connected to, they use satellites to transmit message, right? And it is done via the microwave. It's a radio frequency for transmission, but it is in the microwave bandwidth. Now, in the case of radar, radar applies microwave in the use of this particular machine that traffic police use to detect speed of vehicles on the road. So you can use it to detect speed. Okay, you can use it in air traffic control, control, and that's for radar. Okay, you can use it to detect speed, you can use it for air traffic control, you can also use it for weather forecasting, I believe so. We can use it in weather forecasting. These are the various applications of microwave for radar technology. So it employs microwave to be able to detect the speed of moving objects, to also do air traffic control. Most times when you see that the plane is communicating with the tower, the airport tower, whenever they want to land or when they want to take off, they make use of radar technology to be able to tell whether it is safe to land or safe to take off, and also in weather forecasting. And then finally, for astronomy, microwave is actually used to detect cosmic microwave background radiations. So let's put that down: to detect cosmic microwave background radiations. So these are the various applications of microwave as one of the electromagnetic waves. So which of them do you use? Which one are you familiar with? I'm sure many of you are familiar with how microwave is used for cooking in the microwave oven. You might also know about the satellite phones, but may not know that they employ microwave frequencies for transmission of message. And here we have also talked about radar and astronomy. These are the applications of microwave. The third electromagnetic wave that we're going to be looking at its uses is the infrared waves. Now, infrared could also be, to simplify it, you can use the word IR. Okay, when you see IR waves, we are referring to infrared waves. Now, it is used also in this number of ways. In remote controls, when you look at the remote controls of your TVs, your air conditioners, they are fitted with infrared sensors. Okay, the transducers, the sensors will transmit the information that you are typing from your remote control to the TV, which then detects it and then do whatever you have commanded it to do, whether to change the channel, to increase the volume, reduce the volume, the brightness, change the mode of operation, amongst other things that you can do with your remote control. But the communication link is via the infrared waves from your remote to the TV, or from your remote to your air conditioner. You can always transmit information using the infrared waves. That's in the case of remote control. Okay. Now, another way by which we apply infrared is in night visions. If you're used to watching the Natural Geographic channel a lot, when they are looking at animals in their habitat, especially at night times, sometimes you see they switch to a camera mode that detects heat signatures of the animals. Okay, and the same thing applies to those that watch movies that involve investigations or combat and things like that. You see that they use night vision goggles or night vision cameras. Okay, the way they work is that they are able to sense objects that have a heat signature. Okay, that way you can detect if there is a person in a building, or if there's an animal within a space, by looking at its heat signature through the infrared sensors that are fitted in the camera or the Google that is being used. That's for night vision goggles or night vision cameras. Okay. Now, another application is in thermal imaging, which is used in medicine, in firefighting, and security. Okay, you can use it to tell temperature of a body, especially during the time of, say, during the Ebola crisis, during the COVID-19. People were not sure how this disease could be transmitted, and they see that even by touch you could get infected. So it became a problem as to measure the temperature of the body, because that is one of the symptoms that the disease itself always showed. So you see that even in public spaces at that time, temperature of people were being measured using a particular type of thermometer that does not require direct contact with the body you are taking the temperature. That involves thermal imaging, and it applies infrared waves. The same thing in the case of firefighting and security, where you can detect if a person is within a space when you are securing that particular space, or to detect if there is fire in a space. Whenever there is a fire outbreak and you have the thermal imaging device, you can tell because you would see the heat signature of that fire using the thermal imaging detector. Okay, and it uses the infrared wave as a means of communication. Now, we also have, in case of heating, like there's something known as the infrared saunas. Okay, what you know as hot tub. There are some hot tubs that actually applies infrared to heat up the water molecules, and then you can relax in them, and it applies infrared. So in that case, you are using infrared for heating. And then finally, we can also apply infrared in astronomy, especially when you are looking at distant objects that are obscured by cosmic dust, amongst other kind of dust particles like that. When these bodies are obscured by cosmic dust, you are only able to observe them when you look at it through a different spectrum. The light spectrum will be blocked by the dust. Okay, you can also check out images of the different planets that we know in different spectrums. You will see it in the ultraviolet spectrum, you can see it with the infrared spectrum, you can see it with the visible spectrum. All of them will show you different characteristics of this space object, and you get to appreciate them even better. There are some things that you will not be able to see when you look at it from the visible spectrum that will be detected in the infrared spectrum. So this is why you see that astronomers, whenever they are taking images of space objects, they do it in different spectrum so that they can detect all the possible things that they need to know about that space object. There are some things they won't see in visible spectrum that will be shown in the infrared spectrum or the ultraviolet spectrum. So they use the infrared telescope to also view objects that are obscured by cosmic dust, so they can see more details about that particular object. And all of these are the applications of infrared waves. Now we move to the application of visible light. Now, for the visible light, it's actually called visible because it's the part of the electromagnetic spectrum that is visible to the human eye. Now, please do note that other parts of the spectrum are visible to some animals. Like, for example, there are some birds that are able to see in infrared. There are some birds that can see in ultraviolet. There are some creatures, snakes, rodents, and the likes that can see UV or infrared. Okay, but humans can only see the visible light of all the electromagnetic waves spectrum. So perhaps maybe it's a bit selfish that we are calling it the visible spectrum, since other creatures can see some other parts of the spectrum. But since we are the one naming it, I don't think it is selfish. Well, it's subjective to whoever is discussing it anyways. Okay, but we call it the visible spectrum because this is the part that we can see with our own eyes. I'm talking about humans here now. Okay, and as a result, it has the following applications. Of course, it aids our sight because with the visible light, we are able to see things around us, and it also helps us in the case of illumination. So if you're in a dark place and you need to lighten it up so that you can see things that are within the place. Without light, we cannot see things in a dark space. So we light up places by using light bulb, torches, lasers, and other things like that to help us see those objects that are within the space that we are lighting up. That's also another application of visible light. It is also applied in photography where we use cameras to be able to take images of objects by picking the light that are given off by that particular object. When light waves move from the object to the camera, we can capture the object just as it appears. Okay, you can check out the video on light waves where we talked about cameras in details. You see how a camera actually functions there. It will help you to understand how this is actually done. But it's one of the application of visible light, just as it's also in videography, that is in video recording, which is actually taking multiple pictures and then stack them together such that it looks like a flip book. Okay, you can then record both images and sound together, and then you have what you call your videos. Okay, so that's one of the applications of visible light. Another application is in the optical fiber communication, which is used for by all these telecommunication companies, where they transmit information using optic fibers. Okay, it's a way where you can transmit information using visible light through cables called the optical fiber cables. We also use it in decorations and other things like that. Although we're going to look at this in more detail, I think in the second term of the SS3 curriculum. We'll talk about laser, we'll talk about optical fiber, and we'll look at these applications in more details when we get there, okay? But please note that it is also used as one of the applications of visible light. And then finally, on visible light, another application is in the case of photosynthesis, which aids plant growth. Okay, photosynthesis is a process where plants that have the green pigment known as chlorophyll are able to produce their own food by converting carbon dioxide to glucose in the presence of sunlight. So they use carbon dioxide and water to produce glucose in the presence of sunlight. And of course, there's a byproduct, which is oxygen. Okay, so this is how green plants produce their own food. It's a process known as photosynthesis, and it only happens in the presence of sunlight, which gives the visible light. They are not using the UV that is coming from the sun at that point. They are using the visible light of the electromagnetic spectrum to help in the production of their food and then aid in their growth. And that's it on the application of visible light. Now let us look at the application of ultraviolet radiation. Now, ultraviolet can be shortened using the acronym UV. Ultraviolet. So UV means ultraviolet. So you can see UV rays or ultraviolet rays. They mean the same thing. Okay. Now, UV rays are used in different ways, like in the hospitals and water purifiers. It is used for sterilization. Now, sterilization in this sense is to kill bacteria and other infectious organisms. Okay, like for example, in hospitals, when they put UV light in a space, it helps sterilize that space because especially when they are to perform surgeries, this has to be done in sterile environment. So to make that environment sterile, that is, there is no infectious life within that environment, no life at all within that environment, one thing they can do is to beam ultraviolet light in that space for a number of time, and then it will kill every microorganism, every bacteria that is within that space, and then make the place sterile and safe for surgeries. Okay, like for example, during the COVID outbreak, there was a paper I read where some hospitals applied ultraviolet radiations to make their mask reusable, because that was a time where everybody had to use face mask in order to prevent themselves from being infected with the COVID-19 disease. Okay, and because everyone around the world had to use face masks, it became very difficult to get face masks. It was short on supply all over the world. There was a global shortage of face masks. So people had to improvise, reuse face masks, even produce new face masks using other materials. I remember seeing pictures of people using different kind of materials to just protect themselves. Some people wearing helmets and things like that, just to make sure that they are safe during that time. Now that we are seeing it in hindsight, it looks funny when we look at that picture, but during that time, it was not a funny thing at all. Everybody had to ensure that they were safe, so they had to use different kinds of methods to protect themselves. And I read that a particular hospital put all their used face masks under ultraviolet light to kill whatever microorganism that may be on them, so that it can then be sterile and then they can reuse it. And that way they're able to reuse a lot of the face mask and other materials that they were using to care for people that had the COVID virus. So you see, that's a wonderful application of the ultraviolet radiation. Now, another application of the UV is in tanning, for devices such as the sunbeds or tanning beds. They emit ultraviolet light. Now, you can also tan yourself by staying under the sun over a long time, okay? But if you don't want to spend that time under the sun at the beach somewhere, you can also do that in a tanning bed, because the same ultraviolet light that comes from the sunlight can be done in a controlled environment using the sunbed, where you get the required amount of UV radiations, and that's why it's advised that you don't stay under the tanning bed for too long, okay, because these radiations can be dangerous to the human body when you allow much of it to penetrate the body, okay. So but when you want to tan and you don't want to do it the natural way, which is under the sunlight, you can also expose yourself to UV lights that come from tanning beds, or what we know as the sunbeds, to tan your body. UV light is also used in forensics. Whenever investigations is being carried out in a location where it is suspected that perhaps there is a murder activity that has gone on, or you are looking for bodily fluids such as blood or other things like fingerprints and the likes. When you beam UV light, it helps you to detect bodily fluids, it helps you to detect fingerprints that can help in the investigation that is being carried out at such locations. So you see that different security agencies that do investigations and espionage and the likes always use ultraviolet radiations as part of the gadgets that they use for their forensic analysis of a location, or that is the scene of a crime, okay. Another application is in security. When you go to airport security and places like that, sometimes they use UV radiations for some kind of security detailing, and they also use it in the banks to detect fake currencies, because there is a way they react with UV lights. There are some things that are in that currency that are not visible when you use the visible light, but when you place them under ultraviolet light, you then begin to see those particular things that are in some currencies, and then you can detect which currency is real and which is fake. So these are the applications of the ultraviolet radiations. Now let us look at the applications of X-ray. When it comes to X-ray, it takes application in the following fields. In the medical field, it is used for medical imaging. Whenever a patient has a fracture, such patient is often asked to take an X-ray of the site or the location where that fracture is, so that they can then look at the possible treatment for that case. So when you take the scan of the bones or even scan of organs using X-ray, you are applying X-ray there. You are using X-ray, which is an electromagnetic wave. So you see, in the medical field, X-ray is used to scan bones and also to scan organs. It is also used for security, especially in airport security, where luggages are passed through a particular device fitted with X-ray machines that then scans into the luggage to make sure that whatever is not according to the regulations for airport transportation and things like that will not be able to be passed through. It will be flagged immediately. And once they notice such things, then the airport security can then come in, then check the bag and find the material that does not meet with the requirements of the airport, and whoever owns the luggage would not be allowed to board the plane. So that's how they ensure that wrong devices do not get on the plane. Devices such as explosives, some chemicals that are not allowed to be transported by flight and things like that. They can detect this using X-ray that is used in airports. Now, another application of this is in industrial inspection, like to detect cracks in metals. It is also used for the transmission of petroleum, like through pipelines. Whenever they are doing maintenance to discover if there is any cracks in the pipeline, they also employ the use of X-rays, as it can help detect if there is a crack in the metals that makes up the pipeline. So in all these kind of cases like that, where you have to detect whether there's a crack in a metal, you can do that using X-ray. And then finally, another application of X-ray is in astronomy, where X-ray is used in the observation of high energy objects like black holes. So when astronomers are observing black holes and other high energy objects in space, they employ the use of X radiation. So these are the applications of X-ray. The final electromagnetic wave in the order we have been going through is gamma ray. So let's look at the uses of gamma ray. Now don't forget that this is the one that has the highest penetrating power. It has more penetrating power than X-ray, than ultraviolet, than visible, than infrared, than microwave, than radio waves. It's the highest of all of the electromagnetic waves. Now when it comes to gamma rays, it is used in the medical field in the treatment of cancer. And now there's something called radiotherapy in the medical field, where the oncologist prescribes that a patient be administered a controlled dose of radiotherapy, where such patient is treated to gamma radiation to specific locations in order to kill cancer cells at that location. It's one of the ways by which you can reduce the size of tumors or even kill the tumor itself in a patient. It's a treatment procedure for those who have cancer, some specific kind of cancers anyway. And then there's also another application in the medical field where it is used for the sterilization of medical equipment. It can also be used for sterilization of food, of bandages, and other medical supplies, okay, where such materials is exposed to gamma radiation in order to kill germs and every other living organisms that may be on that particular material, and then rendering it sterile. That is, it is free from any living thing entirely. So those are two applications of gamma radiation in medicine. We also see application of gamma radiation in astronomy, where it is used to detect gamma ray bursts and supernovae. Now supernovae is actually the plural form of the word supernova, which is something that occurs at the dying moment of a star, which usually leads to the creation of a new star and even more celestial bodies that we see in space. It's kind of like what we would call a big bang in space. Well, not exactly the one that we talk about when we say big bangs, okay? So whenever a star is dying out, and when it burns out in a phenomenon known as a supernova. So when gamma ray burst is to be detected, or when you want to detect a supernova in space, gamma radiation is one of the radiations that you can apply to detect such. So these are the applications of gamma rays. Don't forget, I've been able to look at the applications of all the various electromagnetic waves, and you see that each of them have vast applications. Some of them you do use, some of them you've never used before, some of them you've heard of, some of them you're hearing for the very first time. All of these goes to show that electromagnetic waves are very useful to us, and we continue to use them. So if there's anyone you've interacted with, some that you use frequently, like in the case of the microwave that we use to heat up food in the household, amongst other waves that we use, like the radio waves for our television broadcasting, radio broadcasting, and the likes. These are the ones that we are more familiar with. Any other one that I have not mentioned, please kindly drop them in the comment section so that we can interact and get to talk about those particular applications. So this brings us to a conclusion on the applications on electromagnetic waves. But before we end our study of electromagnetic waves, let us look at some questions that you could be asked concerning electromagnetic wave, especially those ones that deals with calculations. Remember that every other thing that we did when it comes to wave can also apply to electromagnetic waves. Things such as frequency, wavelength, the speed is always constant for electromagnetic wave, which is the speed of light. So let's see how we can apply this in questions, calculations that involve electromagnetic waves. This particular question says, a certain radio station is assigned a frequency of 2000 kilohertz. Estimate the wavelength of its radio waves given that the speed of light is 3.0 times 10 to the power of 8 meters per second. Now, to solve a question like this, here's what you do. Now, note that we are given that C equals 3.0 times 10 to the power of 8 meters per second. And then we are given that the frequency F is 2000 kilohertz, that is times 10 to the power of 3 hertz. Now, when we write this, this is basically 2 times 10 raised to the power 3, then times 10 raised to the power 3. That becomes 2.0 times 10 raised to the power 6 hertz. That's what all of this mean, because this is times 10 raised to the power 3 plus then times 10 raised to the power 3 again, and according to the laws of indices you have to add the power. So 3 plus 3, that gives us 6. That's why it's 2.0 times 10 raised to the power 6. And then we are asked to find the wavelength lambda. Okay, and we should know that in electromagnetic waves, since they all travel at the speed of light, instead of having V equals F lambda, we then say C equals F lambda. This is the equation that we apply for electromagnetic waves. For every other wave, the mechanical wave, we apply V instead of C. This will be replaced with the letter V. Okay, so to continue with this, we can then make lambda the subject, which is wavelength. Lambda therefore becomes the speed of light divided by the frequency of the radio wave. And the speed of light is 3.0 times 10 to the power of 8 meter per second. All divided now by, we have a frequency. Frequency is 2.0 times 10 to the power of 6. Now, hertz can also be written as per second. Okay, so you see here per second, cancel per second, and then wavelength lambda becomes 3.0 divided by 2, that will give you 1.5 times 10 to the power of, this is 8, so 8 minus 6, this will give you 1.5 times 10 to the power of 2 in meters. So wavelength here, therefore, if we're writing this in normal form, that will give us 150 meters. That is, the wavelength of this radio wave is 150 meters. And that's how we solve this problem. This is an SSC question which says, in which of the following groups are the radiations arranged in the increasing order of their wavelengths? Now, recall that we remember to arrange the electromagnetic waves in the order revox G. Now, when you have revox G, this order here shows, if you go from gamma to radio wave here, is increasing wavelength. Like this. And in this order like this, from radio wave to gamma ray, is where you have the increasing frequency. Okay, so since we are looking at order of their wavelength, increasing wavelength, the shortest wavelength is gamma ray, while the longest wavelength is a radio wave. Okay, so we now have to look at what we have in the options and see which one follows the order of increasing wavelength. So let's start with the first one here. In the first option, we have radio waves, gamma ray, then X-ray. We already know that this is wrong because the longest wavelength you have is radio wave. So you can't be having the longest wavelength first in a particular order where you want to have increasing wavelength. You are supposed to start with the smallest and then increase as you go down that line. So since we are starting with the longest one here, it means this is wrong. Now, option B says X-ray first. Now, please note, you can actually start from X-ray. You just check what comes next. Okay, since we are only given 3 radiations or 3 waves here, you just have to look at it and see if the ones that follow are in increasing order of wavelength. But here we see we have X-ray, then gamma ray. Okay, and X-ray has a longer wavelength as compared to gamma ray. Gamma ray is the lowest wavelength of all electromagnetic wave, the smallest wavelength. Okay, so you shouldn't be having X-ray before gamma ray if you want increasing order. So that means option B is also wrong. Now to option C, we have X-ray, of course, and then the next one that follows here is radio wave, which has a longer wavelength as compared to X-ray. Then we have gamma ray, which has the lowest wavelength. So this does not even follow either increasing or decreasing order. It's just random. So that means this is also wrong. And then we go to option D, where we have gamma ray. Gamma ray has the shortest wavelength. Then we have radio wave, which has the longest wavelength. Then X-ray, which is longer than gamma ray but shorter than radio wave. So that tells you that this is not increasing order as well. Hence, it is wrong, leaving us with option E. So let's see if option E is correct. Now we have gamma ray, the shortest wavelength. And then next we have X-ray, which actually has a longer wavelength as compared to gamma ray. Okay, so that means we have increased the wavelength here. Then the next one being radio wave, the longest wavelength. So you see, we move in increasing order of wavelength. So that means this is the correct answer. So the correct option, therefore, is E. This question says, which of the following statements is not correct? And we have 5 statements in different option letters from A to E. So let's look at each of them and then identify if the statement is true or false, and then in the end we will then see the ones that are true, the ones that are false. The question itself is asking us to find the one that is not correct, so we are only supposed to pick out the ones that are false in the end. Okay, but let's look at each of the statements and then we determine which one is true and which one is false, that is, which is correct and which is incorrect, and that way we can identify the answer to the question itself. So since the answer to the question is one statement that is not correct, which of the following statement is not correct? We want to see if it is one statement that is not correct, if it is 2 statements that is not correct, if it is more than that, or if everything entirely is not correct. Let's identify that. So the first statement here, which is in option A, says X-rays have a smaller wavelength than ultraviolet rays. So other than the case of grammar here, I don't believe this to be incorrect because the main context here is that X-rays are of shorter wavelengths. Now, the right way to put it is to say shorter wavelength than ultraviolet, but the main idea behind what this statement is still retained even in this statement like this. So that means this is correct because when you organize the electromagnetic waves in order of their wavelength, you know that the longest wavelength is the radio wave and the shortest wavelength is the gamma ray, and X-ray is when you start climbing up from gamma ray. After gamma ray being the shortest wavelength, the next is X-ray, and then up like that until you get to ultraviolet. So that proves that X-ray has a shorter wavelength than ultraviolet rays. So that means this is correct. Okay, now to the next one. Gamma rays are less penetrating than X-rays. Now, many students often confuse this and think that X-ray has the highest penetrating power just because it is used to picture bone structures in human beings, okay, and also every other animal. But that's not correct. Remember that wavelength is the major factor that determines the penetrating power of a radiation. And I did mention when we started our discussion of electromagnetic waves that when you look at all the electromagnetic waves, the shorter the wavelength, the more its penetrating power, which means that gamma ray having the shortest wavelength should have the highest penetrating power. And this is telling us that gamma ray has less penetrating power than X-ray, which is false. So that means this is incorrect. Okay? Now, C says, ultraviolet rays have shorter wavelengths than visible light. And when we look at the arrangement of electromagnetic waves, revox G, we know that this is the shortest wavelength, okay? And we're looking at ultraviolet and then visible. You see ultraviolet is here, then visible here. So visible should have more, that is a longer wavelength compared to ultraviolet. So that means this statement is correct to say that ultraviolet rays have shorter wavelength than visible light. So this statement is correct. Now to option D. Infrared rays can be detected by their heating effect. When we're talking about the uses of infrared rays, I remember I will mention that you can use this to detect heat signature. That tells you that infrared rays has some detection based on their heating effect. You can detect it based on how hot it is compared to every other radiation. It is one of those that can be used to check for temperature. It is one that can be used to check for organisms that give off heat. Okay, when you use infrared radiation, you can even detect fires within a building, as it is used in firefighting amongst other of its application. This is because it can be detected by its heating effect. So that means this statement is also correct. And then finally we have option E that says gamma rays travel in straight line. Now this is not only limited to gamma rays. Every electromagnetic wave, just like light wave, travel in a straight line. So no matter how this particular statement is put, it is still correct. That means in the end we can see now that we have 4 correct statements and only 1 incorrect. So since the question asks that we should identify the incorrect statement, it means the correct answer to this question is option B. This question says, what frequency should a radio wave have if its waves are to have a wavelength of 200 meters? So from this question, we see here that we are given the wavelength of the radio wave, and we denote wavelength with the symbol lambda. That is 200 meters. Okay. Another thing that is not stated in this question that you should know is that all radio waves, all electromagnetic waves travel at the speed of light. So the speed of this wave, which is denoted c, is 3.0 times 10 to the power of 8 meters per second. And we are asked to find the frequency that this particular radio wave ought to have. So what we are solving for here is frequency f. Now the relationship between these 3 parameters is given as c equals f lambda. So to find f, frequency would then be the speed divided by wavelength. Now what does this give us? The speed is 3.0 times 10 to the power of 8 meter per second. The wavelength is 200 meters. Now let's also write this in standard form. So that will give you 2.0 times 10 to the power of 2. 200 is 2 times 10 to the power of 2, and this is in meters. So you see here that meter cancels meter. Now what do we have left? 3.0 divided by 2, that will give you 1.5. Now applying the laws of indices to this part here, you then have times 10 to the power of 8. Since this is division, it becomes subtraction now. So that is minus 2. So the final answer here is that frequency of this radio wave is 1.5 times 10 to the power of 6. And this is in per second, which is the same thing as what we know as hertz. Okay? 1.5 times 10 to the power of 6 hertz. Now, here's a tip for you. When you are working with multipliers like this, do not forget that 10 to the power of 6 can also be called mega. Mega means a multiple of 10 to the power of 6. So we can rewrite this and say the frequency is 1.5 megahertz. So this is just in case you come across questions where you are working with multipliers in mega. right? We've also talked about multipliers before, especially in the SS1 playlist. We did talk about multipliers such as kilo, mega, tera, and every other multipliers that are lesser than that, such as the micro, from micro to pico, and the likes like that. So please check out those videos for a fuller understanding of this. I've just shown you this just in case you come across questions like that, where you are working with frequencies in megahertz, in kilohertz, in gigahertz, terahertz, and the likes like that. Okay, so with this, we've been able to solve a number of questions on electromagnetic waves. Don't forget that during your study time, if you come across any other question that you like some help with, we are always here for you. Please drop your questions in the comment sections of the video, and we'll definitely attend to all of your questions. And please help us to reach many more students like you who need the kind of videos that we make right here on our channel by sharing the video, and also encourage them to engage with the videos by liking them and also dropping a comment. Please ensure that you do this so that we can reach many more like you. We are always here to always ensure that we give you helpful content to make your academic journey even more interesting. Thank you so much for following the video. This brings us to the end of our study of electromagnetic waves. We have more coming your way, so stay tuned. Thank you and bye for now.